right. Austin, you ready to go? You can get your answer up here. I believe we left off on number 44. So I believe that's where we're at in our progress through this. I'd like to think that we could get through 15 questions and be done with this thing today. But I guess we will see how progress goes. Get your answer up. You know what?
I'm still pulling up the question.
Huh?
I'm still pulling up the question.
Okay. Knock it off. Be patient. That's what you're telling me. Be patient.
What number?
44. Very good, Austin. Correct answer. Excellent. Everybody got C. That is the correct answer. Okay. So the CF bonds, easier to break than the CH bonds. When we are dealing with things that are boiling, we're not breaking these bonds in these molecules. Okay. These are intramolecular bonds. These are covalent bonds. Remember, when we're boiling, we're breaking the bonds, or the forces, I guess would be a better term. The forces, we're reducing those forces, or getting rid of those intermolecular forces. So A is definitely going to be out. B is out because this is not a polar molecule. Okay. This is completely symmetrical. So is this. There is no polarity here. So we're not dealing with polarity in terms of this molecule. Although I would say that you could have a slightly polar side on this side versus this side. But that's not going to be the answer. The carbon chains are longer in this one, much longer than this guy. Okay, so because of that, it's going to have a higher boiling point than this one. Okay, their molecular masses are pretty constant here, so that's not going to factor in either as far as LDF issues are concerned. Okay, so all right, so 45. Let's try 45 here. Oh, this is a fun one. Fun, several actually. Let's see if Austin's given us an answer. He has. I've got an answer from David. One more here. David is correct with the answer of B as in boy. Good job. Okay, let's talk about why. Okay, So when we go through this, okay, when we look at this cell here in Z, okay, if we look at the iron here, I'm sorry, not the iron, the copper here. The copper is doing the same thing. So that's a 2+ going to copper. So this guy, this part of that reaction is going to be the same. But if we look at this guy here, this is flipped around because see, we've got our iron here and over here, we've got iron on this side. So do you see how it's flipped around? So if you were to add those together, you would need to reverse the sign of this one and add it to this one. Or you could do your cation anion thing. Yes, ma'am. Oh, that would help, wouldn't it? Austin can see it just fine. The folks that are playing at home can see it just fine. All right, so we're going to end up with 0.78 for the answer there on that one. Okay, can you see? Do you see what I was talking about as far as flipping it around? Okay, sorry about that. Thanks for showing that to me. Okay, let's see if we can do 46. Very good, Austin. Yes, you are correct. And Emma is correct. Good. Okay, so we have in galvanic cells Y and Z, which are the following occurs in half cell 3. So this is half cell 3. So what is actually half cell 3? What material is in there? Iron, okay? Because that's here and here, right? And copper would be half cell 1 then, or half cell, yeah, 2. Copper is half cell 2, and aluminum would be half cell 1, okay? So in half cell 3, in Y, what is happening to our iron here? Well, it's gaining electrons, right? Because it's gone from a +2. So in Y, it's being reduced. And here, it's losing electrons. So here, it's being oxidized. So reduced in Y, but oxidized in Z. Does that make sense? How we figure that out? Okay. So try 47 while I clean up my mess here from all this drawing. Austin, did you answer that one?
Yeah, I did.
C? And C is the correct answer. Very good. Okay, let's talk about Y. So if I increase this guy right here, if I increase his concentration, that means here I'm increasing it this way. So it's going to force this to go this direction and increase this material, this guy. But over here, if I'm adding this guy in, it's going to force it the opposite direction. So it will actually decrease in Z. So increase in Y, but decrease in Z. Make sense? Okay. Let's try the next one. Keep plodding along. See how far we can get. Ah. All right. Yeah, Austin, you are correct. And David, you are correct. Okay, so pH of solutions of the four, we've got these different guys here. For which acid is the value of the acid dissociation the smallest? Okay, well, we automatically, well, we can tell here that the dissociation for this guy is going to be the smallest. And we can pick any of these values. It doesn't matter, but we can see everywhere that acid 1 has the smallest or has the highest pH. Okay, so if it has the highest pH, that means that it has the fewest H plus ions that are coming off out of all of these guys. So therefore, when we look at this, if we talk about HA plus H2O yields our H plus, right? Yeah, H plus A minus, okay? That means that the fewer of this is getting made. So remember, Ka value is products over reactants. So fewer of this is getting made versus this material. So this guy will have the smallest Ka value. Make sense? All right, try 49. Hoping this one should be quick and easy. I think they're throwing you a bone on this one. Austin, you are correct. Everybody's correct on this one. Good. Yeah, so you can identify this guy, especially when you look at the 1 molar concentration here. It has a pH of 0, which means that all of its material, when we went HA plus H2O, it's going this way. And remember, strong HCl is one of our strong acids, so it's going to go to completion here. And I guess it would be HCl. Yeah, it would be Cl here. So this is Cl here as well. So this is coming and it's going to completion, which indicates that we're not going to have much material over here. We're going to have most of it here. So this is our strong acid. Does that make sense? Okay, good job on that one. 50 is the next one. Following species has the greatest concentration in a 1 molar solution of acid 1. So that's this guy. So this is a weak acid. This time our arrow is going both directions at equilibrium. Okay. Okay, so acid 1, we've identified that guy as a weak acid, right? Okay, so I guess I should get rid of the Cl here. So this is a weak acid. So this is what's going to end up happening, A minus here, okay? Now remember, this is a weak acid, which means that a little bit of it's going to go this direction, but a lot of it's going to be favored to this side, okay? So because of that, first of all, are we forming OH when this guy goes in water? Is that one of the products over here? Is OH anywhere here? No. Okay. So A is going to be out. if it's favoring our reactants, since it's a weak acid, if it's favoring our reactants, that means that more of the material is going to be on this side than it's going to be over here. So we're going to get rid of this guy because he's not going to happen. And then the conjugate base of acid 1, this is the conjugate base. This is the acid, this is the conjugate base. He's going to be out as well. So the, I'm sorry, I marked off the wrong one. So D is going to be out as well. So that leaves us with C. Acid 1. Does that make sense, why? Okay. All right, see what you can do with 51 here. Austin, did you answer, honey? Okay. Okay, Austin is correct with D. Okay, let's talk about why. If equal volumes of the 4 acids at the concentration of 0.5 molar are each titrated with a strong base, which will require the greatest volume of the base to reach equivalency point. Remember, we're going to take these and we're going to take them into moles, okay? And that mole value is going to be the same for this guy and for that OH. I guess I should have done OH here, right? Because we're adding a base in here. I should have done that. Hold on. So this is HA plus OH minus. The H is going to go over here and form water. And that's going to give off, the OH went out, the H went with that. So that's going to give us A minus here. Okay. And when these two moles, when these moles are equal to each other, that is the equivalence point. Okay. And since they're all at 0.5 molar, they're going to end up having the same equivalence point. So they're going to require the same volume. Okay. All right, let's try 52. I might just get through these today. All right, Austin, you got one for me? Okay. All right, let's see who's correct here, because 2 of you are either right or 2 of you are wrong, and 52 should be C. So good job here in the room with me. Okay, we get 25 mils sample of 1 molar of acid 1 is mixed with 25 mils of this guy. Which of the following best explains what happens when we drop in some of the HNO3? Okay, so let's see here. If we've got our HA and he's reacting with the OH from here, he's going to be forming water and he's going to be forming A minus. This OH is going to go in with the H here and leave the A minus behind. Okay, so 25 mils of 1 molar acid. Okay, so 25 mils 1 times 0.025 will be 0.025 here for my moles. And here, 25 times 0.5, so 25 times 5 is 125, but I would have had, that would have been 0.5, right, yeah, 0.5. And this is actually 0.025. So that's 3, so, and 1, right? Yeah. All right, let me just double check my math with my calculator. I'm starting to concern myself. 0.025 times 0.5. Yeah, I did it right. Mental math, 0.0125. Okay. So when I drop this guy in, it's going to react with this. I'm not going to have any of this stuff left over. I'm still going to have the majority of it's going to be this stuff. So I would have minus 0.0125. But I've also formed some of this right here. Okay, I've also formed 0.0125 of this in the process, right? So since I have some of this sitting here, when I dump in those hydrogen ions, they're going to attack with this guy, and it's actually going to shift it back this direction and form more of this weak acid. And that'll happen, you know, because we just put a couple drops in there. So it's not a lot. We're just putting a couple drops in there. That'll happen until we run out of these ions, and then it would change dramatically. But just a couple drops isn't going to make a big difference, so it's going to be C. All right. All right, see what we can do with 53. And I've got to do a new thing for that. Is that still your old answer? Mm-hmm. Okay. Very good, Austin. Oh, excellent. Everybody got that one. Okay. So first of all, it's good to identify what Cl is. What do we call Cl when it appears here and it appears here? What do we call that guy? What's he identified as? What's his name? He has a special name. Remember him? Starts with a C.
Remember what it is, but I can't remember the name of it.
Starts with a C.
Chlorine?
No. Meow. Nope. Close.
Cation?
Cat.
Cation? I don't know.
Nope. Catalyst. Oh. Now what is this guy called here? He appears here, and then he is used up here and doesn't appear in the beginning or the end. What is he called? A little bit of vocab review here. Starts with an I.
Intermediate?
Intermediate, very good. Yes, excellent. Okay, so that's what he's called. Now, when we look at our options down here, okay, down here, we've got Cl, okay? Cl is a catalyst, so that is not going to increase or decrease the overall reaction rate. Remember what a catalyst does is it lowers that activation energy. If we have an activation energy that's up here, A catalyst is going to lower that, and sometimes it lowers it by making this a multi-step process, but it's going to lower the activation energy, not the overall reaction rate. So keep that in mind as far as some of your terminology is concerned. So that gets rid of C and D immediately. It's not going to decrease the rate of the overall reaction. I'm sorry, that I meant that as far as the equilibrium constant. It's not going to affect the equilibrium constant. It's going to affect the rate of the reaction because it's going to allow that that activation energy to be lowered, and that's going to increase our reaction rate. So that's A. It should have been your response, and it was, so you did a good job. Okay? All right, let's try the next one, 54. Okay, boiling points. When you see boiling points, what do you think of? It should be the first thing that comes to your mind. We're predicting boiling points. What determines boiling points? Another I word.
IMFs.
IMFs. There you go. That's where your brain should go right away. Okay? So get rid of the covalent character. We don't want to deal with that. Okay? And get rid of that guy. Are we transferring electrons here? When we're dealing with these IMFs, are we transferring electrons? No, they're not going away. So we can get rid of that guy. Okay, so it leaves us with A and C. All right, here we have a spacing issue. Here we have attractions. So when we're talking about IMFs, remember we're talking about some certain attractions here, right? It's this positive and this negative being attracted to one another. Okay, that attraction between these guys is what we're interested in. So when we look at our magnesium oxide here, okay, it's going to have two positives and two negatives pulling on each other versus this guy. Are they talking about Cl? Or are they talking about Cl? Yeah. As opposed to this guy here and this guy here, we've got a plus and a negative. So because of that, and these guys are going to be closer together too, because if you've got 72 and 140 versus 76 and 180, the positive charges here are going to be closer to the negative charges here. So that makes A our correct answer. Okay, see what you can do on 55. I think I gave you guys mental math sheets the other day. Austin, I keep forgetting to give you guys mental math sheets, I think. Help me remember to hand those out to you guys tomorrow, okay? Very good. C is the correct answer. What you're going to look at, if you want this buffer having a 7.5 here, you're going to look at these values here, okay? And imagine that those aren't 10 to the negative. You're going to try to find a value where the pH is closest to this value. And now remember that this is a 3 times 10 to the negative 8, so that's going to come in close to 7.5. But they're going to give you stuff that's spread pretty far apart for something like this, because they want to make sure that you have, you don't have a calculator, so you got to be able to do that mentally. So they're going to give you something that has a pretty decent spread here. The other thing that you need to recognize is that a buffer has to be its conjugate acid and base. So this is not a conjugate, okay? That would be H. The other side of this wouldn't be OH, it would be NO2 minus, okay? Here, this one's fine. This is obviously the answer. And then here, it's going to be, so this one, but the value of this one, it comes in right. So just recognize that sometimes they'll throw you something like this, and you should be able to recognize that that's not even a buffer. Okay, so I wanted to point that out in this example. Okay, see what you can do for 56. Oh, this is a fun one too. Austin, you gonna play? Okay, Austin says D, and D is the correct answer. Let's talk about why. Okay. Did you notice that this container got massively larger compared to these two? Did you see that that doubled in size? Okay. So you need to recognize what that's going to do to your molarity. Okay. We also need to figure out our molarity. They told us that this was 1 liter here. So we know that our molarity is 1 liter. If we count these guys, okay, if we count these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've got 10 of these, and this is going to be 2 molar. We know it's 2 molar because every option here says 2 molar. Okay, so if I've got 10 here, and that's 2 molar, so that means I've got 2 moles in 1 liter. When I come over here and I'm looking at my ions here, and I'm going to be looking at the magnesium here is what I want to be focusing on, because I need to look at that over here, okay, because that's what's floating around in here. And I want to look at the nitrate in this one, because that's what's floating around in here. Okay, so that's why I'm focusing on these ions in here. That makes sense? So over here, how many of these do I have? 1, 2, 3, 4, 5, right? So I've got 5 in 1 liter. We know that this is a liter because we can see, if we eye this up, we can see that they're the same size container. So if over here I had 10 and it was 2 molar, and over here I've got 5, how many moles would that be? 1. Okay. So then I come over here. What's happened to the size of this container? It's effectively done what? What's happened?
It's gone to 2 liters.
Exactly. Yep. So I've got 2 liters underneath here. Okay. Now, my magnesium and my nitrate here. My magnesium, how many magnesiums do I have? 1, 2, 3, 4, 5. So how many moles is that? Well, I didn't change that at all. That's still 1 mole. So what's my molarity here? 1 divided by 2, 0.5 molar. So here I had 2 molar, 1 molar, 2 molar, 1 molar, and a half molar. All right, let's try our next one. Shoot, I don't think go away first. Oh, it didn't go away though. Shoot. Austin, you going to chime in on this one? Oh, C is your answer? Yeah, no, that sucks because it's wrong. The correct answer is B. And if you were to take this and do a line graph, and remember I showed you guys how to do these line graphs, okay? You would find that the natural log of this guy would actually give us a straight line. This is not going to give us a straight line, okay? So just keep that in mind, and you can do that in your calculator. So for example, if we just subtracted here, 38 from 19 is going to be 19. So the difference here is 19. The difference here, 75 and 38, that's going to be more than 19, right? So that's not going to give us a straight line. And here, this is 50. So definitely not a straight line here. Here, the difference is 0.7. Here, the difference is 6, 7, 8, 9, 10, 12, 13 is 0.7. Here, the difference is 0.7 again. Okay, so if you keep that in mind, this guy's going to give us a straight line. He's the only one that's going to give us a straight line if we were to graph it against these things. So B is the correct answer here. All right, 57 or 58. We got 3 more I want to get covered before the end of the day, so we can start FRQ stuff tomorrow. I expect you guys tonight to go home and get ready for the FRQ, and especially Austin's group, so that we can talk about that tomorrow. Because I want to start going through that FRQ data tomorrow. So this calcium and potassium. Calcium is here and potassium is here. And if this is 194, do we get smaller as we go this direction, or do we get bigger? Bigger, right, because we have fewer effective nuclear charge here than we do here. This has 19, this has 20 protons. So you've got fewer things pulling stuff in. So this number should be north of 194. So we're going to look for a number that's bigger than 194 here. So that's going to get rid of C and D automatically. Now we need to figure out, is it going to be easier to pull the first electron away from this guy or from this guy? Which one's going to be easier to pull away? Well, here you've got one electron. You've got 19 hands holding onto it. Here you've got that same outer electron, but this time you got 20 hands holding on it. So it's going to be harder to pull it away from the calcium. So the calcium, the number here is going to be south, is going to be less than 590. So look for a number less than 590, so your answer ends up being B. B? Good. Okay. I'll try 59. I might just get through those. B is the correct answer. Good job. Remember that these dashed lines indicate that we are dealing with intermolecular forces. Intermolecular forces are much weaker, much smaller than, much less than the covalent bond that would be present here. So therefore, there's less force holding these together. The distance increases. If you think of Coulomb's law, as your distance or as your forces decrease, your distance between them increases. So B is the correct answer here. All right, let's try this last one and I will be done with you for the day. You're going to go home tonight and you're going to work on your FRQ material. Ice, ice baby. All right, so when this is a previously evacuated container, okay? So if this is an evacuated container, that means that this material here, when they're going to put in this stuff, it's going to be pure. So initially there won't have been any of this here. So when they initially, after the reaction, okay, so initially the pressure is at 1. It would have started out at 0 here and here. We would have minus x, and these, there's no coefficients here, so we don't have to worry about stoichiometric coefficients here. So this is going to be 1 minus x and x and x. Everybody cool with that? All right. When it reached equilibrium, okay, then it is at 1.2 atm. So 1.2 equals 1 minus x plus x plus x. So these x's subtract each other out. So 1.2 equals 1 plus x. So x is going to equal what?
0.2.
0.2. Okay. So 1 minus x is going to be 0.8, and this will be 0.2 and 0.2. Everybody cool with that? So if we're trying to figure out the KP is going to be 0.2 squared, because this times this, over 0.8. So what is 0.2 squared? Well, that's going to be 0.004 over 0.8. Okay? 4 over 8, you can do that in your head, right? Okay? So that's going to bring you to here. All right, good. See, the math you can do without a calculator. I only picked up a calculator a couple times to confirm that I was actually doing things right, but only to give myself a self-assurance. But we can do this.
See you, Lippy.
Yeah, bye, hun. See you tomorrow.